You can see every time I have to add this. So many checks I need to make. Okay, so this is chromatography, the subject today that will be learning. And we really have to understand the basic technique and theory behind this chromatography, because it is of a very good and important interest for chemical analysis or analytical chemistry. So our learning objectives today is to the principles, how this chromatography works, and the application, of course, that is more tied towards the application, applied scope. And if we show the applied scope for chromatography, you will immediately understand that what is the need for it, but we have to understand the principle first, then we will go to the applications. And the qualitative and quantitative data from this type of analysis or analytical results, and how can we interpret these results, we need to understand as well. And since it is an analytical technique, we have to use it for finding out the unknown compounds or do some investigation, right, and the concentration of it. But identifying and concentration determining is towards something is not common for all the chromatography technique that we are going to learn. But first of basic things we will learn, and thus we will know the principle for this chromatography technique. So we have already finished the weight chemistry, that is gravimetric analysis, right? And then volumetric analysis was the last week. Also the tutorial about the volumetric was last week. And now we are going towards instruments. So can anybody see what is the difference between weight chemistry and instruments? Looking at it, gravimetry, volumetric analysis, acid-base redox reaction under volumetry, and there are instruments, is chromatography, paper, spectroscopy, UV, AAS, all those things that are coming under these instruments. So these two are the main basic, difference in analytical chemistry. Weight chemistry means we have to use the solution, go to the lab, get our hands wet, literally. So that is what we call weight chemistry. But in the instrumentation, we do not need to prepare or do not need to have a lot of the solution, a sample. With a small sample, with the help of high-end, high-tech instruments, we can do the analysis or we can do the investigation. And that is why this chromatography is under instruments, and it is very, important thing for us or for the investigative researchers. So under chromatography, you will see paper and TLC chromatography, GLC and HPLC at the end, but HPLC and GLC will not go much, but we will just introduce you how and what is those things. Right. What is chromatography actually? So this is a technique that we separate different component from a mixture. Like I have a mixture and almost everything you name, one drink, a Ribena, one soft drinks, Coca-Cola, one tea, right? Or a lemon juice you are having, or what else? Ink, or anything. The mixture of substances in one single phase. Phase means that whether it is total all a liquid or all a solid form. Of course, we cannot. Chromatography cannot use solid, but phase, I'm telling about the phase. So when it is a liquid phase and it is a mixture of many different things together, how do we find out what are the things that is mixed together in it? chromatography is a good thing, because if it is a mixture of many things, the gravimetry or volumetry is not going to work. Why? Because gravimetry, we have to make sure that it precipitates, right? But if there are a mixture of a lot of things and you want one certain thing to precipitate, we have to have a very superhuman technique to do that, because other things will also be precipitated. And when we are going to the volumetric thing, right, and this is a mixture and we want to titrate, let's say for titration, we cannot simply titrate one component among the thousand or hundreds of the component in the same mixture. Other will also get titrated, right? So chromatography is the thing that it separates, it like severe the things, the bonds between them, or not bonds, but it separates from one another, and then it is easier for us to identify. And that is why this technique is very much important for our all food and drugs and hydrocarbon in oil, oil and fuel cells, pollutant gases and pesticide and everything, every single thing that we use for our daily lives, right? Chromatography is a very important thing to identify and analyze those chemicals. So on industrial level, or not on industrial level actually, for research purposes, and industrial, of course, industrial level as well, a lot of research depends heavily on this chromatography technique. So that is why we are saying that chromatography should be, we should be very careful in learning the chromatography, the principle of the chromatography actually, so that it will be easier for us to understand the high-end machineries or techniques as well. So application of chromatography almost everywhere it is, we need to use the chromatography. And so the principles of chromatography, it's very simple actually. It has two different phases. Just now I said phases, right? When it is, all of them are in one single status, physical status. So we say it phase. It is either gaseous phase. In the gas, we have oxygen, hydrogen, nitrogen, sulfur dioxide, carbon dioxide, all the things, but we cannot see it. We just see, we don't see gases, but if we look at it, we don't see any difference. Everywhere the air is same. So this is a gaseous phase. In the water, when you look at the water, look at the pond, or in the sea, in the river, you see the water one single phase, but in that water there are so many things is dissolved, right? So we don't see the phases, component, but we only see the phases. So this chromatography depends on this technique of that there are two different phases. One is solid and one is mobile phase. So that mobile phase sometimes can be gaseous, or sometimes it can be liquid phase as well. So, and the solid phase, of course, it depends. Why? What do we mean by depends? Is it depends on the type of chemicals or materials that we are intended to do the analysis on. All right. So there are different types of materials that we can do the analysis, and and according to that, this mobile phase and stationary phase both will depend. So stationary phase is the solid phase that will stay there, and the mobile phase will mobile. It will move actually. Okay, so. And then there is another technique, another principle for chemistry. We use a lot this like dissolves like. And this is not only for chemistry, it's true for our human nature as well. Like dissolves like means the similar thing will dissolve a similar component that has the similar property. So when we dissolve salt in water, salt and water both are polar. in character. So that is so in human as well. I mean, we can remember that we friends get along, right? I mean, best friends get along. That means we are similar minded. When there is a very much different minded, I'm not saying it's bad or good, but we have different choices, we have different interest. So when similar interest people come together, they come and they sit, they get along nicely, and then so that is what we say, this like dissolves like. That means a similar thing will be dissolved in similar thing. So if it is a polar, now these two terms will be you will have to remember, that is polar and non-polar. So when there is a polar, it will dissolve the polar things, but it will not dissolve the non-polar thing. But when there is a non-polar thing means especially stationary or mobile phase. I'm referring to the thing. So if it is a non-polar, it will dissolve the non-polar things inside. All right. So this thing has to be careful. We have to remember these two things. Now, when this chromatography actually, when we do it, that the examples are coming next slides. So how does this dissolve thing happens, that on the solid phase or a liquid phase, like dissolves like, how does it happens? Actually, when the two different thing, like one mobile phase we are using, I think we should go to this for this simple chromatography techniques. So this is a chalk. I don't know whether you have seen this chalk in your school. We do not use this. We use the whiteboard nowadays. But when we were a student, we used to see this chalk. Our teachers uses the chalks, and then we used to make fun with our friends as well. So these chalks, if we dip it in a black ink, this black ink, and also, I mean, it is maybe it looks like that it is from the ancient time, but we ourselves used this type of fountain pen, and some of you still use the fountain pen. I'm not sure how many of you, but we use the fountain pen. So this fountain pen, but nowadays mostly we use this ballpoint pen, right? But previously we had this fountain pen. So this fountain pen, in that the ink for that fountain pen, let's say, the ink is a mixture of different pigments, of different color. Although it looks black, but we have time to talk, to mix, to discuss, not discuss, but to tell you something, that this type of ink, we used to like it because that time when we were young, we did not know, I didn't know that this is like chromatography or all those things. But when we would write with this fountain pen, this ink, and when it dries on the paper, after some time, if you put it in the different type of light, like is the fluorescent light or in the sunlight, it will glare, or it would have some different colors. Sometimes it's golden, silver. So we that amused us, that and we formed of writing using that fountain pen, but it is difficult to maintain because it leaks. So we had to had our many of our shirts and pants were spoiled because of this leak. But that now we understand that, because how does it happen, where it glare, I mean it reflects different type of light because it has different type of pigments inside, or it is a mixture of different type of color inside it. It is not a single color. Although it looks black from bare eyes, if we look at it, it looks black, but it is not necessarily only black. It has a different component, or different color mixed together in a proportion nicely so that it looks black. All right. And Now, how do we know that it is a different color and it looks black? So the chalk, if we dip this chalk inside this black ink, like a small amount of black ink, we put one drop in there, in this, beaker, one drop of this ink in this beaker, and then let it be for a few, maybe 10-15 minutes. You will see that the color separated. All right, the color separated, and then the color is going upward. All right, this all the color, and it got separated. An interesting thing is they are separated in different position. So here we see it is purple, here it is yellowish, and here is green, not green, it is the blue, and here it is faint purple or pink color, right? So why it is at this position, why here this separated in this way, why not all of them are having like this part is pink, this part is blue, and like that, or something like that? Why it is not happening that way? Because this ink, they are mixed of different things, and these different things component inside that ink has a different polarity. All right, they have different polarity. So, and since they have different polarity, they bind different strength. They bind with the chalk when they go up. All right, now, okay, so this is what happens when the ink go up. The water that the ink is dissolved in the beaker, the chalk, since the chalk is dry, right? The chalk is dry, so the chalk will absorb the water, and the water will travel up, because this chalk, when we put it here, right? When first time the chalk is very dry. Consider the chalk is very dry, it's not put yet in the water. But when we put in the water, this side becomes wet first. When this side becomes wet first, this side is wet, but this part is not. This is very dry part. So what will happen? Of course, the water will move to the dry part. The water will move to the dry, most dry, until the whole part becomes soaked in the water, right? That is how it happens. So when the water goes up and make the chalk wet, it will bring along the ink, that the ink is dissolved in the water. Because the ink is polar, so it will get dissolved in the water. Water is polar as well. It not necessarily have to be water, it can be other material or other liquid as well, but for this case it is water. And when it is going along this chalk, going up to the chalk, it is bringing the pigments, and those pigments have different polarity. So they will bind this color. What color is this? This is the pink color, right? No, purple, pinkish purple color, something like that. So this is very much adsorbed to this part. That means it does not like water that much. So that's why this part, they did not travel further with water. But this pink color, it likes water so much that it will go along with water, and it will be staying in the water for longer time. So that means this color, once again, this purple color here, it likes to bind with the chalk more than it binds with the water. And that is why when it comes in contact with the chalk, it holds on to the chalk. And the water, when it is passing by this, let's say that this color holds on to this chalk, and the water molecule is passing through it to go to the top, right? But it does not go along with the water. It holds there. It is staying in that portion or in that position of the chalk. So that's why it does not go move up. So that is why we say that they get separated because of their different polarity, and the way they bound to this chalk is called the adsorption. Adsorption. Here it is. The process is called adsorption. Okay, so on the solid surface, the pigments or the purple color just now we saw, it is holding onto this is by adsorption. There is another term very similar, only we change D to B, it will be absorption. But adsorption is different than adsorption. Absorption is a chemical process, but adsorption is a physical process where it just hold on physically on some surface. It does not make any chemical bond, only physical bond it makes. All right. And since it is a physical bond, it is not a very strong bond like chemical absorption, and that is why it can dissolve. Dissolve means holding on to some surface for some time and then is releasing and going to that water phase again, moving a little bit up and then holding again. So adsorption and desorption, this type of process continues as they go along. So the rate of the movement of the components depends on how strongly that will be adsorbed to the phase, stationary phase of the chalk. As I said that the chalk is just for example, and it can be different phase, stationary phase, and also can be different mobile phase, right? So this is actually a very simple technique and very basic thing for our adsorption. So this blue, or if I can see this pink color, moves further with water so that it is more soluble in water. And it does not hold strongly to the chalk. This color holds less loosely to the chalk than this color. This color holds so strongly that once it goes to the chalk, it stays there, it does not move. Right? All right. So this stationary phase for, the adsorption and desorption process is shown here. So this stationary phase here, the red color is not a chalk here, but is the cellulose or paper, just a paper like this paper. Okay, like this paper is the stationary phase, and then this paper will be put inside, all right, in the water beaker or that is holding or containing the samples, and the mobile phase is the solvent. The solvent can be many things. It can be water, it can be acetone, it can be ethanol, it can be any other hexane, different, depends on what type of sample we are using. So this is the stationary or mobile phase. Once the mobile phase is passing by, and this is some kind of the pigments that is need to be separated. So when it is coming by, it comes along with this silver per atoms. Let's say this is the mobile phase is silver atom. The red color is the stationary phase atoms. So this purple color, is this purple color? Yeah, it's a purple color is the the pigments or the atoms of our interest. So once it is coming along with these silver atoms, it is coming and then it holds on to these adsorption atoms on the solid phase. So it holds there for some time. But once the more water is passing by, right, more and more water is passing by this atom. So what will happen is sometimes it will just loosen up from the stationary phase and move a little bit up, go into the water, move up a little bit up, and then again it will hold to this stationary phase, right? And at some point it will stay there. It will stay there because it does not feel at that point it is a single layer and then it will be strong on the adsorption. But okay, we don't go more detail into that, but I think I made it clear that what is the adsorption, how the adsorption is happening and why they are moving up again. So when it is going up from, let's say we started from here, this is the water level here, and after some point or after some time, this molecule, for this case is the ink, move up to this x centimeter, right? We started from 0, of course, where we start is the 0, and it move up to x centimeter. So this is centimeter or millimeter or whatever, let's say millimeter or centimeter or whatever. So since it move up this much on this surface using this type of mobile phase, so how much does actually it moves, or what does it tell us? It is the retention factor. So by retention factor, actually we will find out, or we can compare the unknown component with a known component. All right. For example, I have tea here, and I'm drinking some tea, and I look at the tea. It looks like very tea color, reddish, or what color? Yeah, tea, red color. But how certain I am that it has all the nutrients or all the antioxidant or whatever I think it is, how to, so I can do the chromatography on my tea, but it moves up a bit, but how do I know that it is that component? I'm looking at it because any component can move, right? Any component will have the retention time or retention factor that it will travel to the solid phase a bit up. I have to use one standard sample for this case. Like for my example, I want to see that how much in the tea, what is the thing that we have in tea? Caffeine. How much caffeine I have in my tea, right? Or do I have caffeine in my tea? And there is actually another thing that I forgot the name, and the tea is it starts with T. The component name starts with T. I forgot that. So let's say caffeine. So how much caffeine I have? I do the what do you call it? Chromatography with my T, and I see this is it is moving up from, this is 0, it's move up to here, right? It move up to here, let's 5 centimeter, 5 millimeter in fact, or centimeter, let's say 5 centimeter. But how can I tell you that, okay, you see this is caffeine I have in my tea? You will ask me, how do you know that this is caffeine? It can be any other thing, right? So what I'll do is, okay, I will do another test with the same stationary and the same liquid mobile phase, but this time I will do only caffeine, only sorry, I will do only, I will put only caffeine in my tea. I mean, sorry, in my experiment. I will not use tea. I will just one single component, only one in the caffeine. And I see that, okay, my caffeine is also giving, because it is not telling you, it does not have a face. It is only the signal or sign or the color it is showing you. So I see the same time after 10 minutes using the same mobile phase and stationary phase, my caffeine and my tea is giving me the same 5 centimeter difference, right? So this is the retention factor. This is how the retention factor is important, and I will use the retention factor to identify my component in my sample. So retention factor means the distance traveled by the component. All right, distance traveled by, oh, another thing, sorry. When I do this, experiment with the chalk or with a paper or whatever, right? This is this is the water level here. Is the water level here, and my caffeine reach until here, and then it is stopped there, but the water reaches until this part. Water, because my caffeine, I put it in the water, or my tea is actually in water. We make tea with water, right? Without water, no tea. So this water level reaches until here, and we started here. This is a zero line, and it reaches to X centimeter, right? X centimeter, and it is 5 centimeter, let's say 5 centimeter cm. So the distance traveled by this component, that is 5 centimeter, it is from the zero line, by the distance traveled by the solvent. Distance traveled by the solvent. So by this retention factor, we will get the identity of our sample or of our components inside our interest. We don't need to, when we say that distance traveled by the solvent, we don't have to keep an eye on the watch that, okay, exactly 5 minutes, 5 seconds. No, we will see that how far the same stationary phase, same liquid phase, same samples we are using, and then after some time we will see how far this sample is traveling and how far the liquid the sample was dissolved is also traveled. So by this ratio we will find, this is the ratio actually, so we find that that ratio is called the retention factor, that is RF, and this RF will be required from now on. It is the important thing. So black ink, again, just now we have seen it is on the chalk for a fun. We have seen it for a fun, the black ink on the chalk. But this time we are going to do it on a paper, all right, on a paper. And this is actually, we should be doing the paper chromatography, all right. So it should be taken into a container, transparent container first. Is better that we use the transparent container, and we cover this container, right? We have to have the cover the container, and this paper is hanging or supported from top, and it is dipped inside. It is dipped inside this liquid, and that liquid should be the mobile phase. This liquid is actually the mobile phase. If it is the water, then this paper should be dipped in the water. If it is the alcohol, this paper should be dipped in the alcohol. If it is any other liquid, it should be dipped in any other liquid. And then we put the samples on the paper in a one drop manner, like one drop here, one drop there. We put one drop there, we put. And then we want to see how this it moves up along with the water. Another thing is very important is that this what do you call it, ink, what we put it on the zero line, right? This zero line is called the zero line, 0 centimeter or 0 millimeter zero line. This ink that we put, it comes in contact with the liquid. It is not totally under the liquid, but it should be somewhere that the liquid starts. It can get in touch. So where we start is 0 is the where we put the ink on the paper, not where the water is. The water may be here or the liquid may be here, but this is not the zero line. The zero line where the ink are. So in this way, we can see that this is not a very ideal, but it looks good. If I would do, I will do it in the lab, this coming lab. I will see that I will put a little bit nearer, probably here. I will put the ink so that it starts early. Okay, so this is a separation of black ink on the paper. Just now on the chalk, we have seen that the color goes up, and this is the same thing is happening, right? It's the same thing happening from the chalk. There was at the bottom there was a purple color, is purple color, and then yellowish color, and then the blue color, and there was the pink color, but pink color is not shown here, or we cannot see it here. Maybe it was different ink than that one we used here, or maybe it was we have to provide longer time so that the more liquid passes through, and then it carries away this ink with it to upward, right? Or maybe the stationary phase was was not correct for this case. Maybe we did not use the proper cellulose, or maybe the cellulose was something. I'm saying that this type of paper, but we cannot use any paper. That has to be a chromatography paper. Okay, so that is the thing. This is the case. Now, for example, a certain mixture of amino acid present in lemon juice separated by paper chromatography. As amino acids are colorless, the developing agent ninhydrin was used. This revealed the amino acid as purple spot on the chromatogram. To help identify amino acids, pure aspartic acid and pure leucine were spotted onto the chromatography paper, right? So this thing is telling that we have to separate the amino acids in the lemon juice. We have lemon juice, and we have to separate the amino acid in the lemon juice. Okay, there are many things can be, but our interest is aspartic acid and leucine. Okay, these two amino acids are actually our interest. So what is the amino acid and what is the aspartic acid? So we'll see it later towards the end of our when we go to organic chemistry at the end of the semester, towards the end of our semester. But now for our chromatography thing, there are these two types of acids to be separated through the chromatography, and the same thing we have done. We put it on the paper, we put it on the what do you call it? The paper is the lemon juice was put on the paper, and one leucine, one aspartic acid also was put alongside at the same distance, from the same distance of the origin or something like that. Oh, sorry, that is not the origin, yeah? This is not the origin, this is the origin. This is the origin, we put it here. This line, along this line we put. So here one we put, here another one we put, right? So it says that which amino acid is more strongly attracted, another way adsorbed, another way bonded to the stationary phase. Which one is the stationary phase here? The paper, right? This paper is the stationary phase. Stationary phase. And the water or the liquid is the mobile phase. So the mobile phase is mobile, going upwards, and it is bringing with it the aspartic acid, leucine, and lemon juice. All it is bringing up towards. Once it goes to this position, we got one spot here. First spot we get, and we also get a first spot for the aspartic acid. But for the other case, we see there is another leucine. It moves up. It goes up 20 units. 20 units means it can be millimeter, or let's say it's a millimeter. So 20 millimeter. So 20 millimeter, the leucine, it goes up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14.5, something like that. 14.5, 14 and a half. For lemon juice, it has two things. One we find at 1, 2, 3 at 3 millimeter. Another one we find it's 7, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 or something. Do a good count, yeah. So maybe 10 millimeter. So aspartic acid also at the 3 units, we see 3 or 3 point something, 3.3 or 3.2, 3.1. And for lemon juice, I got one around 3. So I conclude that in our lemon juice, we have aspartic acid because we get the same retention time. And we know that there are similar type of amino acid. So we have the aspartic acid in lemon juice, but we also see that we do not have leucine in our lemon juice because there is no mark around this 10 millimeter. There is nothing, right? There is nothing, but there is a 13. In lemon juice, there is nothing at 13. So we do not know what is the 13 one. I mean, 13 one, we know that is the leucine. But in lemon juice, we do not have this leucine. We do not have it. We have something at 10 millimeter, but we do not know what is this 10 millimeter. So we do not know what is this because we do not have a standard like aspartic or leucine for this 10 millimeter, right? So we confidently say that, okay, in our lemon juice, we have aspartic acid, but we do not have leucine. And the aspartic acid, the RF, that is the retention factor, is 3.3 units over 20 because the solvent reached until here. The solvent reached until here. And did I mention here, like we can see the solvent reached right here. We can see if we get a close look, we'll see the solvent moved until this part. And we started from here. This is the 0 line. 0 millimeter, zero line. From here until there, the solvent reaches. So this is the solvent maximum solvent front. We call it solvent front. So the aspartic acid reaches to 3.3 units and the solvent reaches to 20 units. So this is 0.17 is the retention factor for the aspartic acid. Now, thin layer chromatography. We will be the same thing we will be having, only the problem with this paper chromatography is that paper, if we keep it for a long time, what will happen? The paper will be dissolved in the water, right? It will dissolve, and once it is broken or dissolved, your whole effort is wasted. So it is not a, very good idea to keep it for a long time. But if the paper does not get dissolved, if we use a plastic panel or plate, then it's better, right? So that's why the thin layer chromatography came on. There is a sheet of metal or a plastic, mostly plastic, and it is coated with alumina or cellulose. It will be very thin coated of alumina powder, aluminium oxide is the aluminium powder, or a cellulose on it, on the surface, only on the surface, very thin. Even you cannot see it, of course, you cannot realize it, but it will be a very thin layer of alumina or cellulose will be there. And mobile phase, of course, the mobile phase will be water or ethanol or anything. So it works the same way. It works the same principle, same thing. Only it can be relied for few more longer time because it will not dissolve away in the liquid. Oh, another thing I forgot to mention that when we will do the chromatography, we should ideally close the lid on the surface. We'll close it. Why do we close it? Because if the solvent is volatile, if the solvent is ethanol, right? If the solvent is ethanol, this one, and if we do not cover it, what will happen is the water molecule will go up. No, sorry, the ethanol molecule will evaporate away, so that you will not find a good solvent front, and it will not be a good experimental analysis as well. So that is why, and also to keep the vapor pressure equal or everywhere this homogenized inside this beaker. The vapor pressure, that means the liquid has a vapor pressure. I'm not sure whether you're familiar with this term, but just remember it. You will have to, if you came to the chemical engineering, then you will have to learn a lot about vapor pressure. It's a very important thing. So the vapor pressure, you will have to, we have to check the vapor pressure first. That is why I'll make sure that is everywhere the vapor pressure is same. So this is another technique or another example, actually, that a thin layer chromatography with a non-polar solvent. It's a non-polar solvent. All right. So an extract from a plant. Okay. So the plant, what do we have in the plant? We see that all the plants are greenish color, isn't it? The green color from the leaves, from the stem, from the plant itself. We look the skin of the plant is a green color. So we have taken the green color or extracted the pig, whatever in the plant, and then we have seen it, done the chromatography on the plant, and we saw that we got it. It gives us a different 4 different color. 1, 2, 3, 4. We got the 4 different colors from the plants. All right, and the distance was shown that it is 60 millimeter. Sorry, origin is 0, so it is 0 millimeter. Of course, origin is always 0, and doesn't matter where it started. If it is even on the scale, it shows 10 millimeter here, right? So probably it will be 70 millimeter here. Still, we'll consider that is the 0. The start point is 0. So the 0, I mean 60 millimeter. The yellow reaches to 60 millimeter. The orange looks like orange. Yeah, orange reaches to 40, and then 27, and this pale green, light green, it reaches to 20. Which one is more polar? Which one is more polar? Before that, we have to because in the plants that we know that there is chlorophyll, xanthophyll, then beta carotene, lutein, neoxanthin. So all those chemical compounds or components are in the plant, right? In the leaves, and it has a lot of xanthophyll or chlorophyll, and then carotene, beta carotene, all those things on the plant leaves it has. We know this one, but now we have to find out which was is what. What is the yellow? What does the yellow represents? What does green or blue or whatever represents? From here we see that it is a 60 millimeter. The yellow color is 60 millimeter. The difference, right? The solvent RF value is 60 for. Oh, sorry. The solvent form was 60. Yellow was traveled to 50. Yellow traveled to 50 millimeter. So now, if it is 50 out of 60 is 83.83. Sorry, 0.83. The retention factor is 0.83, and so on. 0.67, 0.45, 0.33. So now, if we look at it, we see that. We look at it. We see that beta carotene is very near to 0.83. So we understand that there is a beta carotene in our pigment, I mean in our sample, and then the next is 0.63 and 0.45. So 0.63, we don't have 0.63 here, but 0.67. So it's very pretty close. So we can say that okay, it is xanthophyll here. We also have xanthophyll, and then similar way we go with that chlorophyll A and chlorophyll B. Solution 2 problem is asking that since beta carotene travel farthest to the top means it is most soluble in polar solvent, because the solvent was polar, right? The solvent was polar, and the highest it reaches was beta yellow color, the beta carotene. All right, the carotene that it reaches to the highest point. So it should be most polar because the mobile phase was polar. Since it was not stick to that surface, I mean paper chromatography stationary phase, it should be more prone to this. It was more favorable to be with this non-polar solvent, right? It was most to be in the non-polar solvent. So if the polar phase used the polar compound, we'll have the strong ionization. So because of that, we see that non-polar, so the non-polar solvent will bring the non-polar solvent up. It will keep the non-polar solvent with it, and the non-polar material or non-polar things will travel along with this non-polar solvent. All right. So the polarity of the leaf pigment from least polar to most polar will be carotene. So this is the least polar because it came along with this non-polar solvent. So it should be the most non-polar material pigments. And this one will be the most polar. This is the least polar, and this should be the most polar because of that. Now we go for the column chromatography, and I'm going to take a break now. And before I go, I'm going to make some tea for myself. Please go to menti.com. It's very easy actually. And then use these code for your answer. Okay. Sorry. Okay. Please use this. And then please vote faster. Oh, hello, do it faster. I see we are 11 students here, but only 5 or 7 has answered. Please faster, do it faster. You have 1 minute to go. I want everyone to participate. Another 4 students who are not there. Okay, let me start roll calling then. Arlene, are you there? Bilal, are you there? Brenda, Brian, Chelsea, Danesh, Eric, Noor is here. Are you here? Lean, Upati.
Yes, sir.
Okay. Right, so 2 students are not here then. I think I know. Okay, so now we see that the voting is closed. 9 of us has voted. And 5 goes for purple, 3 for yellow, 1 for red. Okay, that's good. So, oh, my camera is off. Now, the thing is, why, let's discuss it, right? Which color is more polar if the solvent is water? What solvent, water is polar or non-polar? Water is polar or non-polar? Anybody has, do we know that water is, whether water is polar or non-polar? Anyone has any idea?
It's a polar molecule, sir.
Okay. Brenda? Noor? Okay, so since water is a polar, then the stationary phase should be non-polar, right? There is no point that I put both stationary and mobile phase the same phase, same polarity, same type. So if it is same type, then it cannot separate. If one is polar, another one should be non-polar. If you are using the mobile phase is polar, the non-mobile, the stationary phase should be polar, or vice versa. So if the water is, water we are using, so water is polar, this stationary phase should be non-polar. Now, like dissolves like, right? So the yellow color, it moves up further, more with the water. It goes up, it goes along good with the water. That is why it has traveled. Let's say this is a start, right? At this point, I cannot take the pen here. So this point, the black point, the most bottom one, is the start point, and the color move up here until here. The yellow color moving to higher, the highest point, it is moving with water, and that is why it is more comfortable with water. That is why it is going along with water. And since it is more comfortable with water, that means it's more polar, and that is the answer for this. That the yellow color is polar because the correct answer is yellow. Enter. Okay. So this is the correct answer. Those three, congratulations. Those 5 or 1, whoever, I hope that you learned now. It's good that we make mistake and then we learn. Right, now we are going to the column chromatography. Right. Column chromatography, and this column chromatography is the same thing, or the principle is the same, only it is upside down. Same with the TLC or the paper chromatography, but it is upside down. Why upside down? Because it is inside a column, just like a burette. What we did in the titration, we put the sodium carbonate or HCl, whatever, in the burette, and then drop by drop we added, right? The same type of thing in a burette type of thing, but for the chromatography, the burette is a bit bigger, a bit fatter, or the diameter is bigger. Okay, so in that way, okay, so for column chromatography is the same. The principle is same. The technique is same. Technique is different, but principle is the same. So in that the column, the burette, the burette of the column. Hold on a minute, yeah. Okay, so the stationary phase is a solid or a solid thing liquid with a viscous liquid or gel in a glass column, such as silica gel. And the silica gel that we have seen, right? If we have seen the desiccator, do you know the desiccator, the glass ball, and then we dry the samples out, put the samples there so it becomes dry. This is called the desiccator. So in that desiccator, we put the silica gel. Oh, you know, right? Silica gel is everywhere in the food or in everything. They say that do not eat, throw it. Yeah, it's dangerous. Yeah, so that silica gel, that type of things, we put it inside as a solid phase. That is the solid phase. Now here in the column chromatography, sometimes we use the glass wool, that type of thing, and silica gel. So, and the mobile phase is as usual the water or acetone or all those things. Those are the mobile phase. Only the thing, the upside down, is for paper chromatography, it is coming from bottom, it is going up. And for this column chromatography, we are putting it from top, so it is with the what do you call it? Gravitation. With the gravitation, right? Gravity force, the liquid is going down through the silica gel and everything. So along it is going down due to the difference in the mobile phase and the solid phase polarity. it will get separated. All right, it will get separated. So yeah, this is it. So here we put the solvent. We put the solvent and the liquid. Put the solvent and the sample. Same. This will be our zero line. From here is a zero line, and of course we just need to open the valve of the just like this burette valve, and then the liquid will go through. It will elute from that. Once it is going through, due to the solid phase, that is a silica gel, for sake of simplicity, let's say it's a silica gel or column, glass wool, it will get separated. The water or acetone or ethanol, it will get through, and then the samples will stick together. Different places. So it depends on their distance from the zeroth line. We understand how polar or how non-polar they are. All right. Only this time, here the higher it is, it looks higher, but actually the same thing actually, because this is the zeroth line here. So this is the closest is the same polarity with the mobile phase. If we are using water here, then it should be the most non-polar component. Component 1 should be the most non-polar if we are using the water as a mobile phase, because water is polar. So this one will be most polar, but this case it will be not for this case. If we are using water. Okay, so from here, this position, we see that which of the component is asking which of the component of the mixture PQ, N and M. There are 4 bands. It got separated. There are 4 things mixed in the sample, and they got separated. So it is denoted at PQ and M and N. P, where is P? This is P, this is Q, N and M. So which of them has the lowest retention factor? We started from there. This is the zeroth line, 0 millimeter, right? And then this is the first one it got. So this is the nearest to the zeroth line. It should be Q, right? Because this is the nearest. It did not get far. It did not get too far. So the distance, it did not travel much. Now, another, just the same technique. Imagine if we have just a little bit this big of a column, glass column, this column chromatography. If we just have this big column, and if we had this bigger column, right? So if we have this column elongated, imagine this glass column, we make it a very long glass, like a few meter, 10 meter long glass. What will happen? What do you think will happen? Anybody has any idea or can tell me that if I take this glass, column to like 10, right? If I take this glass column 10 meter long, 10 meter long glass column, what will happen? Will it be good? Will it be bad? What will happen? Anybody has any idea, or anybody wants to say anything? Your idea.
I'm not sure of what's going to happen, sir.
Yeah, okay, but good, bad, what do you think? Is it good or bad?
I think it's the bad, sir.
Okay. So Pupati thinks bad. Actually, there is a binary choice, right? Either good or bad. Anybody on good side? Or anybody else on the bad side? I mean, not side. I mean, thinks that it will be good or bad. Anybody else? No? Okay. All right. So yeah, this is the thing actually, but it is not bad. It is good. It will be much more complicated, of course, but it will be much more useful and it will be much more sophisticated. And that thing happens. So you see that imagination is very important for us. The scientists saw it that okay, this is a glass chromatography, I mean column chromatography, and it is just half a meter long. If we make it 20 meters, then what will happen? And from that idea, this gas chromatography, this is technology came. Gas chromatography or HPLC, we are going to see. So in the gas chromatography, okay, in that gas, this column, it has a column inside. Here, there will be a column inside. This is a very sophisticated machine. Okay, and it can analyze to a very trace amount, ppm quantity of amount in that in the sample. So here there is a column, but that column is a capillary column. It's a very thin, and it is 100 or 200 meter long. It is coiled inside there. All right. So what it is used for? Liquid high boiling point hydrocarbon or ester spread over the porous support such as silica gel packed in a long, not only 50 meter, 150 meter column as well, sometimes used. So, and the mobile phase in this case is not a liquid, it is a gas. Because when you have to have a 150 meter long column and it is coiled inside, so you know that it has to be very thin. It's like hair thin, and in that inside there is a hollow column, and inside that column there is a thin layer of stationary phase is attached. So the materials, our sample goes through that hole. And carrier gas, nitrogen or argon or helium, mostly inert gas, they are used to carry that sample through that column to the detector or to the place where it will be detected. All right. So the principle actually here that this is a column. This is a column. This column is coiled and is a very long column. And the sample is injected here. And then after that, I open the gas. I allow the gas to flow. So what will happen? The gas will force this sample to go through this column. And when the sample is going through this column, because this column can be polar or non-polar, depends on what do you want to analyze. The column can be polar or non-polar. So let's say the column is polar column. All right, the column is polar, and then we are using this non-polar or a mixture of a sample, a mixture of sample that has both polar and non-polar things in it, right? Just like other sample. So when it is going through this long, very long column, what will happen is along the way, in different parts, it will get attached to this column. Depends on their affinity or depends on their strength to bind, to adsorb on the column. So those who do not bind, or they don't want to bind or bind loosely, they will come first to come to the detector. So you see that making it longer, just to make sure that those sample or the component reaches to detector comes along. It's just them. Two or three does not come together. So one separately they will come, individually they don't come, and then it is easier for the detector to detect what type of sample it is. The detector will not detect by, it doesn't have a nose or it does not have an eye. What will detect is the sample, the voltage difference, how much is the voltage difference, and based on that it will detect what it can be. So the detector will detect, and then we keep the process running for long time. So what will happen is the sample that is, let's say it is bound very strongly to the column, and it does not want to come out. So what we'll do is we will increase the gas flow. We'll increase the gas flow. So the gas flow will increase, and for long time, 5 minutes, 10 minutes, 20 minutes, half an hour, we will keep the gas flow, so that what will happen, even if it is strongly bound, because it is such a small, we need only 1 microliter, okay? 1 microliter. Can you imagine? 1 microliter means one of thousands milliliter is a microliter. So it's a very small amount sample. So even if it is bound very strongly, it cannot stay there long. It has to come, we force them to come out. And that is how we clean this column as well. So GC is very good for using the volatile material, which can be readily vaporized. And that has a molar mass less than 300 moles per liter. Molar mass actually, all right? So environmental monitoring, oil spill pollutants, this medicinal or food analysis or analysis, biotechnology, biochemistry, all those things, GC is good to use, and it will give us this type of peaks. The detector will detect the sample based on their the time that it arrive to the detector, right? It reaches to the detector at what time, at what minute. So this is the detention time. And then another thing is how much of that sample reaches. In a mixture, there is X, Y, and Z, right? But they are not 33% each. Maybe X is 80%, Y is 15%, and Z is 5%, right? So which one is reaching faster to the detector, and how much voltage difference it is causing? This peak depends on that. At what time it reach and how much voltage difference it is making. So the peak will come out at that way. So based on that, we can find out what are the unknown sample, or what are the samples inside this mixture. But still we look, by just doing any sample we cannot find the identity. We need to have the standard sample, right? We are looking for something in the sample. We are looking for whether there is a caffeine in my sample, right? Or there's a vitamin C in my or vitamin D or whatever in my drink. Is there really, or if there is, how much? I am looking for something in my sample, so I have to use the standard of that sample to run first at the same temperature, same time, same column, same detector, same machine. Same amount, 1 microliter for both, right? So this is the same thing we will be using, all right? And let's say that I have done the standard for 20 minutes, right? 20 minutes, I did the run for the standard, and at 15th minute on my standard, I got a peak. Because I have only one component in my standard sample, so I will get only one peak, right? On 15th minute. So from there, I see, oh, actually in my sample, there are of course many things, but I also have numbered. This 3 is actually that standard that I was looking for, caffeine or whatever in my sample. So this is how the chromatography works actually, I mean GC works. And we also can quantify how much is that caffeine in my sample. What we'll do is we will take a different type or different concentration of the same standard. Different concentration of the same standard at the same temperature, same column, same time, I mean 30 minutes, 100 minutes, the run time I will do the same time for the different concentration. For this, what I got at 15th minute, this is for, let's say it is for 25%. 25% of that sample, standard sample I took, and I got a peak of this big at 15 minutes. Now I take 50% of the sample at the same column. I mean, once the 25% sample run is done, I will again start from the beginning with a 50% of the same sample, same instrument, same thing, everything same setup, and then I get another same thing, peak like this big. And I will do 75%, I get this big, right? So from there, I will have an idea that my sample, I have this big peak, right? How big is that compared to this? It looks like it is more than 25%, but less than 50% in between that. So I understand that my sample may be around 40% I have in my sample. So that is how I can quantify. I can quantify our sample. Now it says that the wine need to be tested for ethanol content, and by gas liquid chromatography we can do so. I did the run and I found that it has a relative peak of 82,400 in the wine sample, but for standard 1, 2, and 3, and 4, I did this same instrument, same thing, setup, everything, and I found this. So if I do this, I mean, put this graph on the graph paper, first of all, I will do this, I will use this 4. I will put these 4 values on the graph paper like this and draw a line. It does not have to be very good, as long as it is going straight line, touching all. And then from here, I see that 82,000 is around here. Sorry, it should be around here, 82,000. So from there, I can find what is the concentration of that wine, ethanol in the wine sample, right? Peak area, I put it there. And from there, I drop down on the concentration, percent ethanol concentration on the x-axis, is y-axis, so that I find the concentration of ethanol here. Okay, so please go through it. Another one, this chromatography technique, is high performance liquid chromatography. This is a HPLC, and this is used for much more sophisticated analysis. Although the column is not that big, Okay, column is not that long, but it can actually do a very good and more sophisticated analysis for us. So the same thing is it has a column as well. This is the column for it, and it has an element or solvent is water. The mixture is usually the mixture is used for the mobile phase here, and the separation is based on the polarity of the different molecules that we have. So HPLC is used where we GC we cannot use. It can be used for more than 300 molar mass. Okay, 300 for the. It can be used for the molecule that has more than 300 molar mass, and it does not readily evaporate. It does not vaporize easily. And all the dope test that we do in before the biggest sports activities, the dope tests are done, right? Is this HPLC is used for this case? All right. So it is also it works the same. Principle is the same. Only it can pick up a very trace amount in the blood, because our blood or in urine, that is, blood is a very big molecule and it does not evaporate that easily. Drug as well, that does not evaporate that easily. It remains in the blood for long time, and that is why it is so bad. Even for alcohol, it remains in our blood stream for quite long time. So compare with chromatogram from caffeine standard, identify which soft drink A and B contain the caffeine. So we have two soft drinks, A and B. This is A soft drinks, this is B soft drinks, A and B. So how many of you do drink coffee in the morning? I cannot see you first, but I guess that more than 50% of us drinks coffee, right, in the morning, or maybe multiple times in a day. I usually drink quite many times, 2 times at least. How much caffeine do we take for the coffee? And it's bitter, right? Although, I mean, I'm telling you it's bitter, but I like that bitterness actually. So it's bitter, and the smell is not fragrant, but people say, I feel it's very fragrant. So those coffee, how much caffeine are we taking actually? So soft drinks A, we get a peak at 95-second retention time. For soft drink, I mean, for standard, we get peak at 95-second. But soft drink B, we do not see any peak at 95-second, but it has many other peaks. Soft drink A also has different peaks. But soft drink B has different peaks everywhere, but not at 95. So that means soft drink B does not have caffeine. Soft drinks A has caffeine, right? By this way, we can detect. And how much caffeine do we have in a cola drink? And it is true for any cola. I'm not naming anything, but you know what I mean, right? The cola, the cans that you buy. There are many colas in the market. Go and read the label of that, how much sugar and then caffeine they have. So this is the result of caffeine analysis from the drinks in a 100 milliliter coffee, right? Cup of this coffee and a 375 milliliter cola drinks. If we analyze, we see for an instant coffee in a 375 milliliter of instant coffee drink, we have caffeine, some caffeine we have here. And for this 110 milliliter of the cold drinks, how much is it? Right? We should have a, where did it lost? Okay, let me quickly do this calculation. That 110 times 0.325 is 35 milligram, 35.75 to be honest, 75 milligram of caffeine. And here in 375 times 0.15 is 56.25 milligram of caffeine we have. So it's 35, and so how much is the 1 can of this cola? Right, 375 milliliter of this. Right, so in that 375 milliliter, we have 35. Is it 35? Yeah, 35. Oh, sorry, it is 35. We have 35.75 gram of, not gram, milligram. 35.75 milligram of caffeine in that cola drink that you drink, and in my coffee, it is actually a instant coffee. Probably they put more coffee and put more sugar there, but if we take the coffee at home, like or the black coffee, it does not have that much caffeine probably. My point is that how many colas? 2 colas that we drink a day, maybe 2 cans of cola. We do not get the pleasure of having the coffee, but still we are having the caffeine, and we also have a lot of sugar along with that, because to make it feel palatable to people, to young people especially, they do not like the bitterness, so they put a lot of sugar to make it sweet. So you are taking sugar and this caffeine, but you are not enjoying the coffee, right? So my point was that this is how we can estimate or analyze the very trace amount of different molecules in our bloods, and it goes as well for our drug analysis. We will see in the tutorial next, this coming Friday. Okay, so this is how. So why do we enjoy cola when we can enjoy directly coffee, right? So this is it actually, and this is how it works. And in the summary, the type of chromatography we have, the stationary phase, the mobile phase that will be needed to use. And so this is the thing. So that is it for today. Do you have any question? Anyone has any question?
No, sir.
Okay. Any other question? Anyone else?